So we are live. Thanks to the about 15 people who decided to make the trip to V101 today for the lecture. Thank you very much for being here and for allowing me to lecture in front of some crowd, apart from those who are listening from home. What we're going to do today is to wind up our discussion of matrix transformations. We are going to look at composition of matrix transformations, inverses, and how matrix transformations can be used to implement rotations in a field like computer graphics. So we are going to draw a few things, which should spell danger because I'm not a painter myself, as it should be abundantly clear by now. But anyway, you're going to see some pictures and the matrices that induce the transformations that the pictures are supposed to represent. Before we do that, however, you know what we are supposed to do? We are supposed to warm up, especially because we are still asleep due to the effect of the guy in the sun. So in order to warm up, let's answer a couple of questions by our problem provider, namely Dr. X. So these questions have to do with matrix transformations, so we can slowly get our neurons buzzing by answering questions related to the topic of today's lecture. So here's a matrix transformation for you. It goes from R2 to R2, and it's defined as you see on the slide. My question to you is this a matrix transformation? And if so, what is the matrix that induces it? So while your colleagues here are warming up and thinking about this question, let me put up the scratch pad, and I'm sure that you at home are doing exactly the same thing. You take out your pens and papers, and we write down the transformation that we were looking at on the slide. The transformation said, give me a vector xy. I will return the vector x plus a half of y, y. And my question was, is this a matrix transformation? How would you answer such a question? So if I tell you, okay, assume that there is a matrix that induces this transformation, how would you find such a matrix if one existed? Okay, your colleague, one of your colleagues is saying, well, we try to do the thing that we normally do, which is? Which is what? Sort of, so you want a 2x2 matrix here. Now, if this transformation were linear, how would you find the matrix that induces it? Now, this is a function from R2 to R2. So you need to know, in order to know what this function, if it were linear, and it actually is linear, so let me tell you that. It is a linear transformation. If you were to find what this transformation does to every vector, what would you need to know? You would need to know what it does to how many vectors and which ones. Let me give you a hint. These two vectors have a lot to do with the identity matrix of size 2 times 2. So The identity matrix looks like this. And if you look at the two columns of this identity matrix, they are the vector 1, 0, and 0, 1. And let me tell you that if you know what T does to these two vectors, you will know what it does everywhere if T were linear. Now, why is that? Well, let's say that I know what T10 is, and I know what T01 is. Why would I know what T of A, B does, no matter what A and B are, if T were linear? Why is that? Well, let me give you another hint. I can actually write the vector AB as the sum of two vectors. A0 and 0B. But now, since T is linear, what is this equal to? Hello? Well, what is T applied to the sum of two vectors if T is linear? It's T applied to the first vector plus T applied to the second vector. That's one of the conditions that T must satisfy in order to be linear, isn't it? Okay, so let's keep going. Now, what is this thing here equal to? Well, what is the relationship between the vector A0 and the vector 1, 0? Well, A0 is nothing but A times 1, 0. Isn't it? So this is actually T times of A10 plus what? What is the relationship between 0B and 01? B times 01. But if T is linear, what are these two summands equal to? There is the second, another property the linear functions must satisfy, and namely, this property says that if you feed the linear function with a vector of the form A times X, what is the result? Is A times T of 1, 0 plus B times of 0, 1. And these two equalities here, the ones that I'm circling in red, hold because T is linear. So, but now look at what we figured out. I told you, I know this, T of 1, 0. I know this, T of 0, 1. Well, then I can find T of AB. It's just this quantity. It's A times T of 1, 0 that you know, plus B times T of 0, 1 that you know. So you actually know what T does everywhere, to every vector in R2. Any doubt about this? So in order to figure out what this function, if it were induced by a matrix, does, you just have to put here t of 1, 0, t of 0, 1. Okay, so what is t of 1, 0? X is equal to 1, y is equal to 0, 1, 0. And what is t of 0, 1? It's a half 1. Okay, so if t were linear, this matrix must be the matrix that induces it. Well, is it? It's just a matter of calculating now. We just multiply a vector xy by this a, and we see what comes out. So we had 1/2 0, 1 times xy, and this should be equal to t of xy, which by definition was this. Well, is it? Let's do the matrix multiplication. If we multiply the first row with the column xy, what do we get? We get 1 times x plus 1/2 times y. Bingo. That's what we wanted in the first row. And if we multiply the second row, 0, 1, by xy, we get 0 times x, that's 0, plus 1 times y, that's y. So everything works. That's the matrix. That's the matrix that induces our transformation. Here it is. This is the matrix that induces T. In other words, if somebody tells you, here's a transformation, find the matrix that induces it if one exists, all you need to know is to feed, all you need to do is to feed that transformation with the columns of the appropriately sized identity matrix. In this case, it was the vectors 1, 0, 0, 1, because it was a transformation from R2 to R2. You use the answer, you use the resulting column vectors that you get as columns of your matrix, and if the transformation is linear, that's the matrix that induces the transformation. If you want to double check, you just do the multiplication like we did now, and what you should get is exactly the same expression that defines the function. We've seen a few examples of these in previous lectures, so this is just a recap. Any doubts about this? Your colleagues here are saying no. You're probably saying the same thing at home. But anyway, we'll do more exercises of this type today until people just tell me, no more, please. Okay, here's another question. I give you T, again from R2 to R2, and I tell you it's linear. And I also tell you that T applied to the vector 2, 2 is the vector 6, 2. Question, what is T applied to 1, 1 equal to? One of your colleagues here is saying 3, 1. And that's absolutely the right answer. Why is that? Okay, absolutely. Your colleague is saying, honey, we have the kid. He didn't probably say that exactly, but that's the message. Because if I know t of 2, 2, well, 1, 1 is 2 times 2, 2. And you know that t of 2, 2 is twice t of 1, 1. Why? Because t is linear. So all you need to do is to half the kid. From 6, 2, it becomes 3, 1. You know, this is not true for your average function that you have met in all of your years at school. This is not true for them in general. It's true for the linear ones, because the linear ones are completely determined by what they do on a very small number of points. In this case, we only need 2 points, the value of t in 2 points, even though the domain of the function is uncountably big. R2, there are as many pairs of real numbers as there are real numbers, uncountably large. But since t is a very nice function, you only need to know what t does to 2 points, namely the vectors 1, 0, and 0, 1, and you know what t will do everywhere. Well, it's cool. It's a very, very neat property. Extremely neat. And the reason and how you can calculate that value, well, we just saw it before. T of AB is actually this linear combination of the values of t applied to the vectors 1, 0, and 0, 1. So if somebody tells you what t does to those two vectors, you know what it does everywhere. You don't need to guess. You just need to apply this formula, and out comes the answer. If this is not nice, I don't know what it is. What is nice? Well, I know, but anyway, sort of not within this course. Okay, are we warmed up? And your colleagues here are saying, yes, we are so hot that we are ready to do the new stuff. And of course, I will comply, because I will never say no to my students. Well, I will, but not today. Otherwise, you can take me literally, and then it gets pretty dangerous. Okay, so one of the things that you all know and love about functions is that you can apply them one after the other. That's called the composition of two functions. So the first question that you may ask yourself is, how is this thing defined? So let's see. Let's get our scratch paper out, and let's get two functions. Well, at the moment, this looked like Barba Papa or something of that type, but we'll turn them into functions. So this is Rn, this is Rm, and this is Rk. These are our collection of vectors of appropriate dimension. And we have a function t that goes from Rn to Rm, and you have a function S, just to be consistent with what I had on the slide, that goes from Rn to Rk. Now, whenever you're given two functions whose domains and codomains match nicely, well, you can think of these functions of these blobs that I've drawn as stones in a lake and in a river, and they allow you from sort of by jumping, by following the function, you can go from one stone to the next. And then you can take the next step and go to the third stone. Of course, if you're athletic enough and the stones are not too slippery, you can jump directly from the first stone to the third stone. Now, what is the function that allows you to do that? It's the composition of the two functions s and t, which is usually denoted this way. Now, what does this mean? It means first apply t, and then apply S to the result. Okay, if you want the formula, S composed with T applied to a vector X, what is it? It's S applied to T of X. So you start from X here, you apply T, you get a vector T of X in Rm. But since S is a function from Rm to Rk, you can apply S to T of X, and out comes S of T of X. Well, it's like sequential composition in your programs, isn't it? You first do something, and then you do something else. And I'm sure you've seen it before, somewhere in a previous life, or many previous lives. At least as many as the cats, 9. I'm sort of guessing. 1 per year of your studies. Okay, so this is a very general definition. It applies to any functions. But what if S and T are linear? Is the composition of 2 linear functions also a linear function? And since, in that case, linear functions are induced by matrices, if you know the matrix that induces T and the matrix that induces S, what is the matrix that induces S composed with T? One of your colleagues here is saying it's the multiplication of the 2 matrices. And that's absolutely right. Let's see why. So function composition, if you're talking about linear functions, corresponds to an operation that you all know and love about the matrices that induce those functions. And that operation is multiplication. So let's see why that's the case. So if S is linear, if T is linear, you know that T is induced by a matrix. What does this mean? This means that T of X is actually going to be A times X for every vector X of the appropriate size. So in other words, you want to find out what T does to a vector X, multiply A by the vector X, where A is the matrix that induces T. And you know that that matrix actually exists because linear transformations are exactly matrix transformations. So there is a matrix that does the job of T. So excellent. You also know that S is linear. What does this mean? This means that there is a matrix B that has the property that S of X is equal to B of X for every vector X of the appropriate size. So, what is S composed with T applied to X? Well, we just defined up here what this function does. It says, first of all, apply T to X, and then apply S to the result. But hey, what is T of X? T of X is actually A times X. We just consult our visual memory. It's written there. That's what it is. It's A times X because A induces the transformation T. Yeah, but what is S applied to a vector? Well, it's B times that vector, where B is the matrix that induces the transformation S. So this is B of multiplied by A of X. But matrix multiplication is associative. This means that we can actually bracket it as we like. In particular, we can bracket it this way. But hey, what is this? It's a matrix. It's a multiplication of the matrix that induces S with the matrix that induces T. And what does this matrix do? It induces the composition of the two. Because look at what we found out. If you want to figure out what S composed with T applied to X does, multiply X by the matrix B times A. And this works for every X. This means that B times A is the matrix that induces the composite transformation. Fantastic. That's another benefit of linearity. Instead of dealing with this function composition, which might be strange, we just do a matrix multiplication and we are cool. So function composition is nothing but multiplication in disguise. Well, at least if you're dealing with linear functions. So if we go back to the picture that I was drawing here, actually we could do exactly the same with matrices. Here we had our matrix A, here we have our matrix B. And this is nothing but A times X. This is nothing but B times A times X. Bucks. It sounds like the code number for a British Airways flight. So there we are. So if somebody tells you, can you tell me what matrix induces the composition of a bunch of transformations which are linear? All you need to do is to find the matrices that induce each one of the transformations, and then you multiply them together and you're done. So you see, we are seeing the same concepts, matrix transformations, solving systems of linear equations, elementary row operations, reappear over and over again. You can reuse them to do all kinds of interesting stuff that apparently these concepts were not defined originally for. When you see a situation like this, spider senses tingling, as Spider-Man would tell you to do, because you're in the presence of something important. So if somebody tells you multiply these two matrices together, you're doing a lot of things. You're also composing functions, amongst others. So it's a humble operation, but very useful. So far, so good? Because now you know probably what I'm moving on to, namely inverses. Could it be that this computation of the inverse of a matrix, provided the matrix was invertible and square, otherwise it isn't invertible in general, well, it isn't invertible, could it be that that operation actually has a meaning for functions as well? Let's see. So suppose somebody tells you, well, here's my space Rn for some n, and I have a function t that goes from Rn to Rn. and I tell you that T is linear. Now, let me sort of try to scrape the cobwebs from your memories of a previous life. And I ask you, what does it mean for T to be invertible? Okay, your colleague is saying, when there is a function, let's make it blue, that goes in the opposite direction. And usually this function is called T to the minus 1. Okay, you can think of this as being an undo button. So you apply T, but then, well, perhaps you're not happy with the result, you press undo. And the undo will give you back the original argument to which you had applied T. So what does this mean? This means that if I run T first, and then I do the undo transformation T minus 1, I should get back exactly the same thing that I had before. So if I start from a vector x, I apply T to it, and then I undo the transformation that T has performed, I get x back. That's what the undo button does, isn't it? I don't know you, but I certainly use the undo button. And I hope there was more of it. I cannot use it here, for instance. It's a bit difficult to do in a live show because you cannot rewind time, unfortunately. But there you are. I can sort of undo something. Now, this also works the other way around, actually. Why? Because if I am here, and I go somewhere, and then T is the undo of T minus 1, just as T minus 1 is the undo of T. Now, is every function invertible? A function is invertible if such undo transformation T minus 1 obeying these two properties actually exists. But is every function invertible? Well, your colleague is saying no. And you might remember from some previous lives that not all functions are invertible. And in fact, in real life, we have experience of this. So if you have an aquarium, you heat it up, you get a fish soup. But if you cool down the fish soup, you don't get an aquarium back. You get a cold fish soup. Okay, that's an example of a function that is not invertible. I don't encourage you to try that at home with your own aquarium in case you have one. Now, in general, there is a condition over functions that precisely tells you if that function is invertible. And I am sure you've seen it before. But if you don't remember what it is, it doesn't matter. I'm just supposed to ask you, what is it? What functions are invertible? Let me give you a hint. We've seen these functions in this course where we've used them to measure the size of sets. These are the bilateral agreements. No, the bijective functions, I guess. So in general, actually, the only functions that are invertible are the bijective functions. But here we're dealing with linear transformations. Can we characterize invertibility of a function by means of another notion of invertibility? Absolutely. A function T is linear if and only if it is induced by a matrix. So your colleague said, well, I mean, what's in a name? A function is invertible if and only if the matrix that induces the function, the linear function, is invertible too. And that makes a lot of sense. Why? Because if T is linear, then you know that there is some matrix A such that T of x is equal to A of x for every x. Now, what I want is a function that does the undo of this transformation. Well, if A is by any chance invertible, then there is a matrix A minus 1 that has what properties? If A is invertible, it has to be a square matrix, your colleague is saying, but this is cool because I'm looking only at functions that go from Rn to Rn. And these functions are induced by square matrices. Absolutely. So if A is invertible, there is a matrix A minus 1, which has the following properties. If I do A minus 1 of A times A, what is it that I get? I get the identity matrix. But that's also the same that I get by multiplying the matrices the other way. So in some sense, since the identity matrix actually does nothing to any vector that you multiply it with, you just get that vector back, A minus 1 sort of undoes the transformation to a vector that A does. So couldn't it be that actually A minus 1 induces the inverse of the matrix of the transformation T? And you know, it does. Why? Because if we say that T minus 1 of some vector x is actually A minus 1 times x, let's see what we get. So let's see what is the result of applying T followed by T minus 1. Well, actually, in this case, it's T minus 1 followed by T applied to a vector x. What is this? This is T times T minus 1 applied to x. But hey, T minus 1 is defined to be A minus 1 times x. But what is T? T is defined as A times the vector I'm applied to. But what is this? A times A minus 1 is actually the identity applied to x. And if you multiply anything with the identity, you get it back. So actually, T composed with T minus 1 is the identity function. And by a completely similar calculation, you can also figure out that this is the same as T minus 1 composed with T. Yes, of course you can ask a question. Yes. Okay, so the question is, and let me highlight in red the step that your colleague is referring to, so that he can also complain if it's not the right one, but I think it is the right one. So he's asking, how do you justify this step? Well, as follows. A minus 1 times x, that's the vector that T is applied to. But T is a linear transformation which is induced by the matrix A. So applying T to a vector is the same as multiplying A by that vector. And that's why that equality holds. But then since A times A minus 1 is actually the identity, because A minus 1 is the inverse of A, then we get x back. So what is the message? The message is that if somebody tells you, here's a function t, it's linear, and it's a function from R2 or Rn to Rn. How do you figure out whether that transformation is invertible? Well, you compute the matrix that induces that transformation, and then you find out whether it has an inverse. If it has an inverse, then that inverse is the matrix that induces the inverse transformation of the function you were giving as an input to begin with. How do you compute the inverse of the matrix A if one exists? By using what? Okay, your colleague is saying, is this enough to find the determinant of the matrix to see if it is invertible? Finding the determinant will tell you whether the matrix is invertible or not, but we have not covered determinants in this course. So you can use the elementary row operations. But yes, sort of, you can use the determinants if you know about that. But we haven't covered the determinants in this course, and we will not cover the determinants in this course. So, yes, question. Mm-hmm. Your colleague is saying in the lab assignments, in the assignment 5, don't we need to use the determinant to solve one of the answers? I'm pretty sure you don't need to. But let me double check. If you need to, it's only for the matrix 2 by 2, and then in that case, it's on a slide. But anything you can do, I mean, it's about computation of inverses, you can do it with the elementary row operations. That's your method. Okay, any doubts about this? So let's look at one example. So that you will see that. So suppose I tell you, here's a transformation. It's from R2 to R2, and it does the following thing. Oh, sorry. I love T so much that I'm getting carried away here. The transformation T says, give me an X, give me a Y, I'll give you X 2Y. Question, is this invertible? And you don't need to guess. Your colleagues here are saying, yes, it is invertible. And what is the inverse? So let's do it stepwise. Okay, so what is the matrix that induces this transformation? The matrix that induces this transformation, we simply find out by plugging in as inputs to T the vectors 1, 0, and 0, 1. If I plug in 1, 0, I get 1, 0. If I plug in 0, 1, I get 0, 2. So that's the matrix A that induces T. Does this matrix have an inverse? Well, yes, it does, because, I mean, it's nearly already the identity. The only thing we need to do to turn it into the identity is to do what? We multiply by half the second row. So this means that the inverse is this one. And what is the function that corresponds to this transformation, that is induced by this transformation, by this matrix, sorry, A minus 1? Well, that's A minus 1 times xy, which is nothing happens to x, because if we multiply xy by the first row, we get the dot product is going to be x plus 0, so that's x. And then we have y. Which in hindsight is what you expect, because if the transformation t doubles the value of y and leaves x unchanged, what is the undo operation? The undo operation is to halve y. So if your kid eats too much and doubles its size, then what is it that you need to do? You just halve the amount of calories that he gets so that he gets back to normal. I don't need to do this with my daughter, but there you are. It can happen. So I sense that there is need for a break now so that people can really absorb all this interesting stuff that we've done in the first part of today's lecture, and we'll be back online after the break. Yes.